Good morning. Good morning, Clara. Good morning, Brian and Nathan. Good morning. Good morning. Thank you for joining me. Always. Okay. I think as we were talking yesterday, we will try to review the entire chapter 2. Okay? That's when we will have the limits review. This section will be also quite helpful for the midterm, for final, for any assignment. Okay, that's what we have. That's the list of the sections, and I hope you look at the section 2.6. Limits with trigonometric functions, but a specific limit. We will do it. And also we will also cover limits at infinity a little. I mean, we will cover, yes. And then we will look at more like, practical examples. What else? Because why I'm not seeing this. And then we will also have a couple of questions from section 2.8, the indeterminate intermediate. I kind of interchange that words. Intermediate value theorem. Indeterminate forms, that's different story. Intermediate value theorem, like a value between the other two values. Okay, let's see what I have. Okay. Okay, that means I just list the limits laws, limits properties. Yeah? We have to be able to use them, apply them at the right moment. And at the bottom, we have a direct substitution property. If the function is polynomial or rational function, or in general, we can say if the function is continuous function, because polynomials and rational functions are continuous on the domain, wherever they are defined. And then if the number A is in the domain, then we can just use the direct substitution. Okay, we have to remember about the indeterminate forms. Yeah? Then we have to do a little bit of algebra, simplified, and then use substitution. Okay, and let's actually look at this. That's me for now. We just need this information. Please tell me really quickly what are the following limits are. Looking at the graph and the limits. I hope I list them correctly. No typos, we will see. Okay, that's how this function, this nice function, behaves as x approaches -4. -4, the limit is, yes, thank you, we can see the limit is 2. It is quite, it is quite a feature, quite a behavior of the function, that sharp turn, this sharp like corner, but we will talk about this in chapter 3. But for now, even if it's smooth function or the sharp corner, still the limits exist. We don't have discontinuity. The limit is the same as the value. Okay, x approaches -3. What we can say? What is the limit? The limit is, I'm looking at the limit is -2. Of course, we're looking at this. Perfect. What about limit at -2 as x approaches -2? Yes, the limit is -4. Okay, not this one. And what is the value? What's the value at, yes, the value is -3. Okay, what about the value at -3, actually? What about the value at -3? Do we have the value? Does function have the value? No. Yes, thank you. The value does not exist. We can see no solid dot. If we will draw a vertical line, no intersection. Okay, what is the limit at 0 as x approaches 0? Just the value. Yes, function is continuous at 0. That means maybe that point. Yes, we can say -3.5. Okay, what about limit at 1? Oh, that's interesting. At 1, we will put positive infinity. What about 2 from the left-hand side? Now we have this section. 2 from the left-hand side is -1. 2 from the right-hand side is +1. I can make it this. And what about the limit at 2? If we have to answer, no, does not exist. Thank you. Perfect. Okay, because two different one-sided limits. Okay, what about limit at 3? I just added limit. Yeah, I think it's just the value. We may say 1.5. It's fine. 4 from the left-hand side. X approaches 4 from the left, 2. Perfect. 4 from the right-hand side. Yes, negative infinity. And, oh, I suppose to say 4. What about the limit at 4? Because this is always the conclusion. The limit does not exist. Perfect. And what about the limit at 5? I just added. We may look at 5. I think it's 1. Just continuity. Okay, that's from the graph. Perfect. Let's keep working. The next exercise, we have to find the limits, but we just have the formulas of the function. We may recognize all of them are the basic functions. We may draw a function, we may sketch a graph, or we can just do algebraically, right? That means, for instance, all of the x's less than -2, they will follow the parabola. They will behave like function x squared. Okay, that's n equals to 2, equals to -2. That's what is the limit at -2? Let's maybe start from the left-hand side. We will use, yes, I can maybe use the formula. We will use the formula. It's continuous function, then we can just substitute. -2 squared, it will be 4. We can draw it, but yeah, let's see. What about -2 from the right-hand side? Which formula we will use? From the right-hand side, we can see it's the second piece. That means I can maybe put the formula. It's not, we're supposed to substitute right away. And then when we substitute is -2, 7. Yes, because will become 4. Okay, yes. And now, what about, and then 4 and 7. Then what is happening at -2? The first limit. The first limit does not exist. Okay, I will write it down. Okay, what about limit at 1 from the left-hand side? Okay, we did this section. 1 from the left-hand side. 1 from the left-hand side, we will, which formula we will use? Please tell me. Yes, correct. Because this is sitting on the left-hand side, and we can just substitute. We can see no indeterminate forms. No, I think everything is continuous. Okay, 1 from the right-hand side. Which formula we will use 1 from the right-hand side? We have to have an interval from 1 to 10. Yes, we will use that cube. Actually, plus, minus actually. X minus 2, 1/3 plus 2. Okay, when we substitute 1, it is just 1? Yes, like this line is just telling us what is happening at 1. That means value at 1 is 5. Okay, limit from the left and from the right-hand side actually is the same, even using different formulas. Then we can state that this limit exists. Okay? Actually, did I compute correctly? -1 to the power of 1/3 cube root of -1 is -1 plus 2, it is 1. Okay, and then let's look at 10. 10 from the left-hand side. Which formula we will use for 10 as x approaches 10 from the left-hand side? Is also the cube function. Yes, thank you for typing. And what's the value? 8 cube root of 8. 2 plus 2, 4, Please check my arithmetic. And then 10 from the right-hand side, we will use the last one. Yes, thank you, Lara, thank you. And 10, 5, oh, also 4. Excellent, excellent. That means this limit exists. And are you okay to draw the function? I think you will be okay. You can check the solution on the slides. X squared, no problem. Line with negative slope, no problem. Just the dot at the level 5, just the line with the slope 1/2. And this one is the cube root. I hope we know function cube root of x looks like this. Cube root of x. Or we can say x to the power of 1/3. But this one has a little bit of transformation. -2 means that we will shift along the x-axis 2 units to the right, and +2, we will shift 2 units up. Well, that means this is a good point. That means 1, 2, 1, 2. Okay. In the graph, will look like, it's just shifted. Oh, I suppose to draw a little bit more precise, because it's important thing happening at that point, at the dot. But again, chapter 3. Okay, but the blue part, but we can only take the blue part between 1 and 10. I mean, this will be 1, which actually, what is the limit at 1? I think I have to, you can see it's telling me I have to be a little bit higher. Okay. Because the limit at 1 is 1. And then limit at 10 is 4. 10. Okay, so we will only take that part, the green part. I can erase everything. Okay, it's that cube function we have to shift, and then we have to restrict the domain. Okay, and the rest of them you can add. You know the connections. At 1, both of the functions will connect, the line and the third degree. I mean third degree, like in the cubed root. At 10, they will also connect that line and the cubic function, yes. And which one? And actually at -2, they have, what's the name of this behavior? If we have 2 different limits on 2 different sides. This one will be, oh yes, it's definitely discontinuity. What's the type? Jump, because it's 2, yes, thank you. The jump discontinuity, 4 and then 7. Okay, you can finish this, because let's look, we have more, the other exercise. Okay, it's me now. Let's try to answer these questions. And again, what we need to remember about the indeterminate forms, and we have to also remember about this 1/0 or 1/big, 1/small, 1/big. We know the result, we know the answer. Okay, assume that the limit as x approaches 6, f of x is 4. Okay, that's, we know that is 4. For each part, calculate the limit or determine that the limit does not exist. If the limit is positive or negative infinity, we have to say, because we know that we can also say does not exist. Okay, what about the first one? The first one, limit of the power is just the power of the limits. I don't know if I have to rewrite like this, but maybe we can just, and then we know that this limit is 4, it's basically 16. Okay, what about this? Limit of the quotient could be the quotient of 2 limits. And we can see section 2.3, limit at 1, and the limit of the function. What is the answer? Yes, it is 1/4. Actually, limit of the constant is just the constant. Because if the function is constant 1, it's always 1. As x approaches 6 or 7 or 8, always the same, 1. 16, 1/4. Okay, what about this one? Limit of the product is a product of two limits. Limit of this one and limit of this factor. Of course, the same x. X approaches 6. And this, what is the first limit? Limit of x as x approaches 6? Just direct substitution, right? Okay, and this one is 4. Okay, now, limit of the quotient is the quotient of two limits, yes, for part D. But because I didn't say this at the part B, we have to make sure that the denominator is not 0. If the denominator is 0, then we cannot really use directly that property. As we can see, limit of this one, let's do a little bit faster. It is 4. And when we actually substitute, what we're gonna get? Let me do it. 4/0. Oh, okay, and it's definitely positive 0. We don't have to really specify the side because we're squaring. Even if it's 6 from the right-hand side or left-hand side, even if this quantity is positive or negative, we will square it. That means it's 4 over small number. What is a constant over small number? It's a big number, of course. I can rewrite like this because I like to say 1 over small. It's a big number. That means it's actually a big number. Okay, let's say this. Infinity. Yes, nice limit. Okay, what about E? What will be the answer for E? Please tell me. Limit of the difference is difference of two limits, and limit of the quotient is the quotient of two limits. That means I am just trying to do direct substitution. And we again have 0 in the denominator. That's why we cannot really compute separately. Yeah? This is really informal, we know. Yes, that means in this situation is negative. It's still 1 over small, it's big, but that negative number will affect the final answer. Thank you. Negative infinity. Very good. That's actually times. Okay, but this one is big. This one is big. Big is infinity. Okay, and what about the last one? Limit of f of x, it's 4. And then we have 6 minus 6. We do have 0. But can we really say if that 0, that small number, is positive or negative? No, because if 6 is from the, again, as soon as we see 0, we have to think. It's not 0, it's a tiny number. But now, positive or negative? If 6 is, if x approaches 6 from the right-hand side, this will be positive. If it's from the left-hand side, will be like 5.999 minus 6, the quantity will be negative. That's why we cannot really say this limit, different one-sided limit, okay? Because we don't know. It's positive or negative infinity, but different from both sides. At 6, the limit does not exist. Okay. It's a vertical asymptote and function will go up and down on both sides. Okay. You're good. You're earning lots of points. Okay. Oh, nice exam type question. Suppose that the limit as x approaches 0, f of x over x equals to 10. Calculate the limit as x approaches 0 just of the function f of x. What answer you will tell me? Let's see. This is f of x. Do you know the answer? You probably know. That's we know, okay, we know the answer. The answer is a finite number. Definitely 0 in the denominator. That's the problem. Then what form we expecting? If we have 0 in the denominator and the final answer is a finite number, non-zero finite number, then what is the only option that we may have it? We want to cancel out that 0 in order to get the finite number. That's what we're expecting on the top. What we're expecting on the numerator, zero. Yes, that's actually good. That's actually good example. Function f of x could be, for instance, 10x. Or actually, yeah, that's actually, I can maybe create diff, but yes, that's, and 10x over x, we will cancel out that x, that's 0. That means we have to see the indeterminate form. That limit must be 0 because the final answer is a finite number. Okay? Really nice question, and really like testing the understanding of the indeterminate form and the result. Okay, good. Yes, even, yeah, I like the example. That means 0 over 0. Good. This limit must be 0. That means this is limit and this is limit, of course. Maybe I can, let me, limit of the function. I'm not saying about the value. As x goes to 0, as x goes to 0. And that means both of them, they have to be 0. Okay. Now, what about this one? Exercise number 5. Suppose that the limit of g of x as x goes to 0, it is 0. Okay, now let's calculate this limit, g of x over x squared. What is the answer? Limit as x goes to 0, x squared, limit as x goes to 0, x squared. I just want to have 3 examples. Because what we can figure out, g of x, yes, g of x is sitting in the denominator, in the numerator, right? Oh, I don't know. That means this is g of x, g of x. And let's think what I want. I want from you to give me possibly an example of the function g of x that the limit will be 0. Yes, for instance, because we know this. Okay, that's what function at 0 is 0. As x approaches 0, the function also has the value 0. Can you give me an example? Yeah, parabola, this will be easy, x squared, yes. Because this limit, actually I can maybe put this g of x in the numerator right away. Because we may have 3 different situations. Okay, x squared. G of x could be x squared. And then what is the limit? It is 0 over 0, but the limit is, we see right away, the same zeros, x squared over x squared. When we cancel out, the limit is 1. Okay, but now, can we possibly put, did somebody set x cube? Cube root of x, but let's say x cube. Let's say x cube will be easier for calculation. It's also 0 over 0, the g, yes, g of x approaches 0. But what about this situation? We may cancel out x cube over x squared. We will end up with this, and the answer is 0. Yeah, we remember from yesterday, because we have triple 0, multiple like of 2, like double 0 in the denominator, triple 0 in the numerator, we still end up with 1 0, and 0 on the top is fine. Okay, and now what do you think? What function? Yes, we still expect 0 over 0, but possibly just x. Yeah? And let's say from the right-hand side, we may cancel out 1 over x, and what is this limit? Yes, what is this limit? 1 over small number, and it's from the right-hand side. 1 over small, it is big. That's what we can see. Yeah. We don't know what is, we know that g of x is 0, but we may create lots of scenarios. 0, 0, 0, x squared, x cubed, and just x. What is the final answer? Of course, E. We cannot figure out. We do have not enough information. Yes, and also nice question. Okay, another one. Oh, maybe this one we can leave it, or maybe not. Because, I mean, even if we will not go through live, through all of the questions, you will check that presentation, okay? You will not miss any question from this presentation, because you may see this again. Okay, we have nice rational function, or I mean ratio of two functions, because it's root, square root. And what happened when we do the direct substitution? Limit as x approaches -4, and the direct substitution will be 16 minus 16, and then 16 minus 7. Of course, we're not even surprised. Okay, I think it's 0, and then, yes, 9, square root of 9, 3, 3 minus 3, 0, 0 over 0. Okay, do we know what we have to do? In order to find that common 0, we will rationalize denominator. Really good. Let's try. It's a nice, we will do it. We will multiply by the conjugate of the square root. That means I will copy this square root and 3, and I will put plus. This was minus, and this is plus, and the same on the top. And we're gonna distribute the conjugate expression. In this example is in the denominator, but we will not distribute the other one, because otherwise we will lose the 0. And actually, where is the 0, the factor? Let's factor out x, and we can see this is 0. X plus 4 at -4, it is 0. Okay, can you simplify denominator? When we FOIL everything, it will be x squared minus 7 minus 9. Am I right? And we can maybe say x squared minus 16, x minus 4, x plus 4. Okay, that's in this is the common 0. We may see it. Let me copy one more time. Okay, actually this is parenthesis, because we need a nice solution. And that's how you're presenting the solution on your written homework. Limit, as soon as we have x, we have to carry on with the limits, and now the 0 is gone. Now it's just the direct substitution. What's the final answer? -4, 16 minus 7 plus 3, and -4 and -4. -4, 3 plus 3, 6, -8. 6 over 2, 3. Am I right? I cancel out. I hope the answer. Please check. I don't remember the answer. Yes, thank you, Laura. Thank you. Okay, beautiful. Beautiful algebra. Okay, let's keep working. Section 2.6, trigonometric limits. Let's check if we know. Did you check that limit? What is the limit number 1, 2, 3, 4, 5, 6, 7? As x approaches 0, sine of x over x, it is 1. Yes, please check, because I'm using the squeeze theorem to prove this. And we don't have to really know the proof, but it's nice to see where this comes from. Okay, that means sine of x over x. Interesting thing, it is 0 over 0. And for this one, it will be quite challenge maybe to try to do algebraically to find the common factor. No, it is one, but I use the squeeze term and I prove it, and you can watch it later. Okay. Okay, this limit is one. Also, the reciprocal is also one. It's also one, no problem, because but the first one is the main one, because this is proven, and then it's just like some variation. Because if I will let's say this one. Oh, I cannot write that high. Normally, we will rewrite as a one, and then we can flip it. Yes, limit of one is one, and limit of the denominator is also one. Yeah, because of the first. That means the first, excuse me, the first formula is like a property, like a tool, yes, that we're using. Okay, now, what about number three? Do we know number three? And also, I can tell you, okay, let's do number three. Let's do number three. What do you think? If it's also one. And that's what I was gonna, some of the textbook, some of the, they will say that this is also the formula. It's like tangent of x over x, as x goes to 0 is also one. But again, the main one is sine of x over x. Just to make a general statement, the only two functions, trigonometric functions, sine and tangent, will give us this property, no any other functions. Because, for instance, what is cosine at 0? Cosine at 0? What is cosine at 0? No. Cosine at 0? Unit circle, or maybe the graph? Cosine at 0 is 1. 1, that's cosine, right? At 0 is 1. Cosine at 0. Sine at 0 is 0. Yes? 0 over 0. Tangent at 0 is 0, but not cosine. Okay, that means sine of x over x and tangent of x over x. This is 1. But the same, in order to, not really, like in order to prove this, we can rewrite sine of x over cosine of x. That's tangent. And we still had x in the denominator, and we can see this is 1. That's, we will end up 1 cosine of x. X is 0. And that's what I asked. What is cosine at 0 degree? It is 1. That means the limit is 1. But I still use that property. Okay? We may, of course, remember, okay, tangent of x over x as x approaches 0 is also 1. Yeah? But the main one, the main formula, the main tool is sine of x over x. Okay, what about number 4? It's the reciprocal. We can do respectively the same like number 2. It's also 1. What about number 5? Yeah. Yes, it will be 2, but we have to be careful, because what happened? Again, getting back to this property, the first one, if I'm saying sine of x over x as x approaches 0 is 1, I mean that x, that quantity, and this quantity must be identical. Yes, and it's 0 because we know we may have x may be squared, x cubed. It's still sine of 0 over 0, but it has to be identical 0. And now we don't have identical. You see, we have 2x and x. That means properly, yes, the answer is 2, but let's prove it, how we get that 2. Sine of 2x, this is like, we cannot split this, divide by x. I can say this is 1. I can say that this limit with 0, it is 1 if this is identical quantity. That means I will actually force it. I will put 2, but since I multiply the denominator, I will also multiply somewhere numerator. But I will just grab this. This is my property. And now we can see identical quantity. Now this is 1. Yeah, sine of 0 over 0, sine of identical 0 over 0. It is 1. And what's left? The 2, 1 times 2, this one. That's the reason that we have 2. Okay. Okay, what about number 6? Yeah, we may probably, okay, we have sine of 3x and we have tangent of 7x. That's what we're missing in order to say that this limit is 1 or this limit is 1. What we're missing? We're actually missing the entire, even the variables. We're missing that input, that argument. That's in order to say that limit is 1, of course, x goes to 0. What is that? What is that angle? 3x? We're missing 3x. Then I can say this is 1. But since I put it 3x in the denominator, I multiply, then I have to do it in the denominator. I mean, numerator and denominator. Denominator at the bottom. Denominator and then numerator. But I'm only taking this, and this is 1. And the same, I need 7x. And since I multiply the numerator, I will multiply also the denominator. But I'm not canceling out. Then this is 1. And what's left outside the loops? These extra expressions. And what is this limit? It's still 0 over 0, but we may see the zeros that we may cancel out. Okay, that's mean this is, and I really want you to think, because for instance, number 7 is a nice exam type question. And what is the answer? What is the answer for number 7? Who can tell me? Of course, I'm trying to trick you. I can do it now, but on the test, oh, come on, just try. 5 over 20, of course. Just no constant beside the angle, am I right? It seems like we just have to multiply by a constant beside the angles. I mean, yes, but we have to be careful. Okay, we have to be careful. Yes, one constant is missing because we definitely need to see 5x in the denominator in order to say that the limit of sine of 5x over 5x, that's 1. Yes. Okay, that means yes, I definitely see the answer 5 over 20, yes, which will be not right. We remember cosine of 5x. 5x times 0 is 0. Cosine at 0 is 1. And since this is product, we can ignore it. That's when we theoretically, we have sine of 5x over 4x. Because cosine is 0. If it's addition, we will keep it, but it's product. And then what we need, let's maybe use, actually no. In order to say that this limit is 1, I need 5. That's the constant. I will multiply by 5. And what's left? 5 over 4. Because this loop is 1. Sine of 5x over 5x. 5 was left outside and 4. This limit is 5 over 4, not 5 over 20. That's, yeah. Of course, that's my trick. Okay, please, please be really careful. We can see we did all of the examples that kind of lead and forced us to think how to solve number 7. Number 7 is exam type, okay? Remember cosine. No. Okay, good. Let's leave it this one. I mean, this is kind of the essence of 2.6. Okay. Oh, that's another nice, but it's probably easy. What's the limit? Still 2.6. Section 2.6. Sine of x plus tangent of 3x over x as x approaches 0. This one is nice because what we can do, we can, oh, let me write a little bit lower. Yes, when I share the screen, I cannot write on the top. What is this limit? Yes, I think it is 4 because we may rewrite as a 2 fractions. And this one is definitely 1. And this one, we will do the tangent of 3x over 3x is 1, and the 3 stays. The answer, of course, is 4. But please be careful with like just playing with the coefficients. Because if it's cosine, then we have to be careful. Okay, good. Also nice question. Okay, another nice question. Another exam type question. Oh yes, you will see similar question. Okay, for what values of the constant c will the function f have a limit as x approaches 2? And we have piecewise defined function, different on the left, different on the right. In order for the limit to exist, both of the limits, both of the one-sided limits, they have to be the same. That's we have to say limit as x approaches 2 from the left must be the same as limit as x approaches 2 from the right-hand side. Okay? And we have to solve the limits. No value, because we can see no equal sign. Which formula we will use on the left-hand side? The top or the bottom? The first or the second? Of course, the top. That means what is this limit? And this is, of course, the point. It's really nice. X goes to 2 from the left. Sine, and now look at the angle. C times x minus 2 over x minus 2. Limit as x goes to 2 from the right, and then, oh, absolute value. That's also important. Okay, and the thing is, if we do the direct substitution, what we getting on the left-hand side? Sine of 0 over 0. That means 0 over 0. We're getting this, 0 over 0, 0 over 0. Really risky, yes, to maybe cross multiply or something. No, 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 no. We really have to take care of one side and then on the other side. And as soon as we get finite numbers, or as soon as we eliminate zeros from the denominator, then we can maybe cross multiply, or we will see. Then we can solve for c, basically, because we need the value c. Okay, what is this limit on the left-hand side? Limit on the left-hand side? What is missing to say that this limit is 1? What we missing? I mean, we're missing that coefficient or quantity c, because we have x minus 2, and we remember this sine of the entire angle has to be seen in the denominator. That means we will missing c. Then I can say that this limit is 1. But since I multiply by c, I will also multiply the numerator. I mean, actually, this limit is c. Yes. Because we have sine of c x minus 2. And I only have x minus 2. I multiply by c, and then I multiply the top and the bottom. Then this is that c. Okay, that's actually nice, because the left-hand side limit is just equal to c. Now, what is the limit on the right-hand side? Yes, for the absolute value, we know that we have to rewrite without the absolute value. Yeah, it's definitely 0 over 0. And we know how to rewrite the absolute value. Yeah, let me check. If we have positive quantity, what is absolute value of 5? What's the absolute value of 5? It is just 5. Absolute value of 6? 6. Of 100? 100. But now, what is the absolute value of negative 5? Can I say negative 5? Of course not. Yes, you giving me the correct answer. But if I copy this answer, I just copy, of course, that's incorrect. and I know that the quantity inside was negative, I can hack this and put negative. Then it's correct. If it's positive, I can ignore absolute value. But if the quantity inside is negative, I can copy this quantity and put extra negative to make it positive. That means let's check. Is this quantity 2 minus x positive or negative? If x approaches 2 from the right-hand side, what is the number 2 from the right-hand side? Then we will have but 2 from the right-hand side, yes, it will be like 2.001. 2 minus 2.001, yes, Laura, thank you. It will be negative quantity. So now what we will do, let's actually write this, maybe this is fine, I have no problem, but quantity 2 minus x, that was inside the absolute value, is actually negative. I am making positive. Now we did the absolute value, now we can do the algebra. Let's simplify, maybe distribute, but we know where this negative come from. It's like this, like -5, because the quantity is negative. Okay, x minus 2, and when I distribute negative, it will be -2, negative and negative x is positive x. Excellent, it's just the same thing, the limit is 1. Limit on the right is 1, limit on the left is c is 1. Yes, okay, nice 2 limits, really nice limits. Yes, okay. Okay, I just love these problems. Okay, let's keep working. Continuity. Yes, that was the section, I think 2.4, but I will combine with 2.5. Basically, the function is continuous if the limit and the value is the same, and the number, of course, is in the domain. Yeah, then no problem. Limit exists, value exists, and they are the same. We still know the difference, yes? We still know what is limit and what is the exact point. Okay, and for instance, this is nice question. Find the value k, but I can leave it, maybe this one for you. Let's just set everything. Find the value of k that makes function f continuous at 2. Because this formula is defined everywhere, but not at 2. That means everywhere, but not at 2. At 2, what is the value at 2? Value at 2 is exactly equals to k. That's what we want. We want the limit as function approaches 2 equals to the value. Yes, value is k. We can see this, k. It's exactly at 2. But limit, you will use this formula. Okay, 2x plus 5. And what method you will use? Because it is 0 over 0. Okay, and of course, please do not say 0, yes? No. We really have to have a reason. Maybe it's 0, but I don't know if we're really multiplying the zeros here. Okay, you will multiply by the conjugate, simplify everything, cancel out. This is that factor. That is the problem. We have to find out on the top and cancel out. And then you can substitute and get the value k. Okay, but this is the settings for continuity. Okay, I can leave it, this one. Oh, nice. True statements, true or false, yeah, because which statement are true, all of them could be false. Or all of them could be true. Okay, let's quickly answer. Let's think. If the limit as x approaches 1 of f of x over x minus 1 equals to 10, then the limit of f of x must be 0. Do you think it's true? Yeah, we did similar. Because let's see, 0 in the denominator, 1 minus 1, then finite number. What we have to have on the top? If it's 0 we have to have indeterminate form. That means, yes, this is true. That's true statement. Okay, if the limit of function f of x at 1 from the left-hand side is infinity, then function f is discontinuous at 1. Yeah, we can draw this. 1 is definitely a vertical asymptote. This is for part. And from the left-hand side, maybe like this. Yeah. Because even if we have infinity on the right-hand side, or maybe negative infinity, or maybe even finite number, we don't know. Definitely it is discontinuity. We have discontinuity. Okay. And what about the last one? If f is continuous at 1, then the limit is the same like the value. Of course, section 2.4. Just the definition of the continuity. Perfect. Yet true and false questions are always a little bit. Okay, let's keep working. Okay, I can leave it this one, easy. And that's what I wanted to do. Okay, that's me. Let's finish session, hopefully. I mean, no, not now. We have 10 minutes with these questions because that's section 2.7, limits at infinity, which you can also look additionally for some video. I have a nice video for you, and I'm explaining everything in like more details. Okay, but this one I can give you just the shortcuts. Nice tool. Okay, what about the first limit, 1 over x? 1 over big number, of course, is 1 over big. Now we have, let me write this. It's a small, informal, 0. And we can picture the graph. Oh, I cannot write on the top. 1 over x looks like this, hyperbola, in the first and the third quadrant. And as x is getting bigger and bigger, because x goes to the infinity means that x is like increasing without the bound. Then function is approaching that line because 1 over like bigger and bigger number is gonna be smaller and smaller, okay? Lower and lower the values. Okay, 0. And now, please check my section 2.7 because it's quite, I'm explaining the algebra meaning. But now let's see. Number 2. Do you know the answer for number 2? All of them are limits at positive or negative infinity. That's them. Okay. We can definitely see that x plus 3 goes to the infinity and parabola goes to the infinity as x goes to the infinity. This is indeterminate form, the other one. But now, if we do a certain mathematical algebraical trick, we have to always look at the leading function, leading terms. Okay, leading terms. That means x is the leading one, and we may try to like factor out. This will be 1, this will be 3 over x. Okay, this leading in the denominator is x squared. 1, 5x over x squared, 1 over x squared. Because when I distribute back is the same expression that we started with. And now we can see 3 over big number is small. If I cancel out 5 over big, small. 1 over big, small. And this is 1, 1. And now only this matters. X over x squared, when we cancel out, it will be 1 over x. 1 over big, it is small. That means it's also 0. Okay, infinity over infinity, but we get 0. That's what is important. We always have to look at the leading terms. Only leading terms matters when we calculate limits at infinity. Okay, we can see algebraically, and you can check for more like algebra, like proofs or algebra like calculation. But limits at infinity, we have to look at the leading terms. That we will because the other one, we can see they will become 0. Then eventually they will like disappear. That's we have to look at the leading terms. And now, if denominator has a greater degree, if the denominator is winning, always the limit will be 0. Okay? Because we can always end up with a constant, 1 or constant over x, because denominator has more greater power. We will cancel out and we will end up with that big number in the denominator. 1 over big is small. That means if the denominator has greater degree, always limit is 0. Okay. What about if the degree is the same? Yeah, we will actually cancel them out, x squared over x squared, and the ratio of the leading coefficients will matter. That means this limit will be, can you tell me? Yes, please watch this will be 5. Because it's, what about number 4? Find the leading. This is leading, and this is leading term. They are the same with respect to the degree. Yes, and it's also infinity over infinity. 5 over -4. Perfect. What about number 5? Number 5 goes to negative infinity, but we can see we're squaring because this leading term and this leading term is the same. So we can say negative, wrong, because this will be squared, even if it's negative infinity, goes to infinity. This will go to the negative infinity. Am I right? Okay, but what is the final answer? This is still indeterminate form. The final answer is still the same. Doesn't matter in this case because we're squaring that infinity, positive or negative. Okay, now what about number 6 and 7? 6 is different. Leading term and leading term. Yeah? We know that the rest of them are algebraically not, they will disappear, not important. Now, that's the leading terms. And what is happening when we cancel them out? We still have constant, but we will end up with x. We will end up with x because x cubed over x squared is x. And then, yes, x is big number. X is infinity. Constant is not important in this, in this case. That means now the general statement, if the denominator is winning, if the denominator, numerator, if the numerator is winning, always infinity or negative infinity. Because can you tell me the answer for number 7? Leading. Let's look at, and now we are at negative infinity. 5x cubed over negative x squared. Let's cancel out. Negative 5 over 4, limit is at negative infinity, and we end up with x. That's we have negative 5 over 4 times negative big number, negative big. Then that negative and this negative will give us positive. Yeah, that means actually constant is negative. Yes, if the constant will be positive, then the answer will be negative infinity. But the constant is also. Okay, that means that's how we can do. If the denominator is winning, always 0. If it's the same degree, finite number, non-zero finite number. If the numerator is winning, positive or negative infinity. Okay, that's the shortcut of 2.7. I also have this, but what we can do, this one, it's also kind of like a battle between numerator and denominator, but we have to know the relative rates of growth. For the polynomials, it's easy because the degree will determine this. For different function, like logarithmic, exponential, it's different. That's what we can do. I think you have the video. I have the nice video, which is called relative rates of growth, and I'm explaining which function grows faster. Yeah, really nice. Some of them are really fast, but I can give you the summary. When we have power function, x to the power of a, x to the power of b, this function will grow, yes, like increase faster, but I'm just saying everything is at positive infinity as x increase. If b is greater, that means that's algebraic function, power function. Now, faster function is exponential. A to the power of x, b to the power of x. Of course, again, b is greater. That means 2 to the x versus 3 to the x. 3 to the x is faster. Yes, relative rates. And something that is maybe the fastest, but we will look at this later, it's x to the x and something else. We don't know. We can create something. But what I want these power functions, exponential, and then one of the slowest function is the logarithmic function. Let's say log base A. Okay, that's the slowest function. That's mean logarithmic, power function, and exponential, right? And now, whichever is winning, then we know if the denominator is winning, 0. If the numerator is winning, positive or negative infinity. In this case, will be probably positive. I mean, no, depends on the coefficients. And if they grow at the same rate, yes, then it's non-zero finite number. Okay, can you tell me, like looking at this maybe really quickly, because they are just by looking. And then we can finish the session. Okay, what about this one? Natural log of x over x. Which function grows faster? And I can say this is the relative rates of growth. Okay, I think x, because we can see x to the power, yes, x grows faster, denominator is winning, 0. X squared or e to the x? Of course, exponential, then denominator is winning, 0. Power function, no. Exponential function, 2 to the x over natural log. Numerator is winning, infinity. X to the power of 200 versus e to the x. Even if it's 200, maybe at the beginning, x to the 200 is higher, but exponential will take a lead. Yes, I can say exponential grows faster than any power function at infinity. Okay. This one will be a finite number actually, because we may rewrite it. Let's leave it this one for you can because you just need some property. What about this one, number 6? Yes, because 6 to the x grows faster, okay? And what about, oh, I think I'm supposed to have x, because that's weird. 6 to the x versus 3 to the x, infinity. And what about number 8? Number 8 is interesting. Let's find the power one, the fastest one. This one, yes, because now I can list anything and you will just pick the fastest. And what is the final answer? Nice exam type question. Please give me the correct answer. And actually, but let's look at the 4 e to the 3x and negative 8. Oh, I cannot. Let's look what I circle. 4 e to the 3x and negative 8 e to the 3x, the same leading function. Yeah, that's the fastest based on the relative rates. Yes, we will just take the ratio of the leading coefficient, 4 over negative 8, negative half. Of course, nice exam type question. Okay, let me finish. Oh no, it's way too, too late. Okay, thank you very much. And this was, this is nice, section 2.7. And please, if you have only time, please explore the additional videos. Like, I mean, I cover everything, what we need in chapter 2, but please check for a little bit, maybe more detailed explanation, okay? Okay, thank you very much and enjoy, yes. We will not have session tomorrow because you can look at the small videos, but you know everything to complete your assignments. And yes, next week will be the last week before the midterm, okay? Okay, thank you. I'm so happy. I'm so happy that you find this helpful. The videos, if you look at the homepage, in the middle, you will see like a link, Mat 140, Kasia's YouTube videos. I think that's the title. Okay? Okay, thank you. And yes, see you next week. Thank you.